I want to thank the organizers for this invitation. I've never been to Maryland. This is great. It's nice to see some snow finally in winter. Just to get myself situated, how many of you here are first or second year graduate students? And then the rest are upper grad students or postdocs? Okay, how many of you have done like vapor, liquid, solid, or chemical vapor deposition growth of nanoscale materials? Okay, a couple of you. Good. So I hope to talk about and teach you about just the basics of vapor, liquid, solid growth and chemical vapor depositions, and how these two growth methods are used to make quantum materials at the nanoscale, and why you would perhaps want to study quantum materials at the nanoscale. Some of it will be focused on topological materials, mainly because I work on them, and some transition metal chalcogenide layered materials. So expanding it a bit from just the 2D nanochalcogenides to include topological insulator, topological crystalline insulator nanostructures. So why nanoscale? I want to sort of motivate you why you should also pay attention to studying these materials in the nanoscale. It's mainly because you get emergent properties because of the confinement effects, right? The quantum mechanical effects arise at the nanoscale when your wave functions of the electrons are about the size of the materials. Then I'll talk about nanowires. Okay, how do you grow nanowires? Primarily vapor, liquid, solid growth. And there's a one killer app, I think, for nanowire structures for topological materials, and that's in the context of quantum computations using topological superconducting nanowires. Then the second part of the lecture will be about making layered materials. Graphene, of course, was the starting material back in 2004. That was mechanical exfoliation, top-down approach, but we'll do chemical vapor deposition. Okay, so why nanoscale? Some of this we all know. Band structure engineering, right? We know that the band gap get larger as you confine your materials. It's a classic particle in a box type problem. As you shrink the size of the box, the levels, right, the spacing between the levels get larger, band gap then increases. And in some way, as you shift around the band edges, it can have also indirect to direct band gap transition. We know this for molybdisulfide, and that makes it big difference in optoelectronic applications because there's a good coupling between electrons and photons that way. At nanoscale, especially for a single layer of materials, two-dimensional materials, you can do a quite effective strain engineering from the substrate. Unlike bulk, in bulk, it's very difficult to apply strain through the substrate, right? But here, that's pretty effective. And that can be another way to tune your band structures. Now, for topological materials where we care about the surface electron states, going to nanoscale is good because you're just simply going to remove as much bulk as possible, right? So you're trying to enhance the surface effects that you're looking for. Emergent properties. Some examples of emergent properties at the nanoscale in the context of topological insulators. As you make the topological insulators thinner and thinner, the top topological surface starts to couple to the bottom topological surface, and you'll then gap the surface state. Okay, so for bismuth selenide, that's the transition happens around 5 quintuple layer thick materials. Tungsten ditelluride, semi-metallic TD phase layered material. As you get down to a single layer, there's a little bit of structural distortion, and you get a quantum spinol state, right? So that's a topological state that comes around in a single layer limit. So there are often emergent properties that we want to look for at these nanoscale. And many of these materials, it's the surface electronic states that are interesting, so we just want to remove as much bulk as possible. Hence, nanoscale materials. So for topological insulators, here's the band structure of topological insulators, right? Bulk semiconductors if you make it right with little defects. Surface states, here's a direct dispersive electronic states for the surface. Surface to volume ratio increases at the nanoscale. Because it's small, I can tune the Fermi level effectively through bottom or top gate, just like in thin film. Thin film can do both, right? Thin film gives you the same advantages of nanoscale structures like nanowires or nanoribbons. I think another advantage of using nanostructures, let's say nanowires, is the fact that, so here's an example of actually angle resolved photoemission spectroscopy band structure measurement of bismuth selenide nanoribbons, okay? So this is an ensemble average measurements where the bismuth selenide nanoribbons are randomly placed on the silicon oxide substrate, and you're just getting an ensemble average measurement. Because the direct cone is cylindrical, you can resolve the surface states very nicely, whereas the bulk bands are blurred because the ribbons are oriented in random orientation. Now the distinct advantage of using nanostructures is the fact that you can do interferometry experiments on your surface electrons, right? So the cross-section of the nanowire per se is very well defined by the underlying crystal structure, right? So if it's cubic, you're going to get a rectangular cross-section. And you can then subject your surface electrons to circle around the surface, feed magnetic field, which will then change the phase of the electrons, and now do interferometry experiments, okay? So here is a phase-sensitive measurements you can do in nanostructures, where the interferometry setup comes for free by the virtue of the fact that your system is already at the nanoscale, where the electrons will start interfere with each other. So if you take care of your materials very well, you will see this. So this is bismuth selenide nanoribbons. This is grown by, I would say, metal catalyzed chemical vapor deposition. So here is a nanoribbon in pink. So we're threading magnetic flux through the wire. Electrons are circling, and they're going to interfere because their phase is changing as a function of magnetic field. And you'll see these oscillations, and they're called Aharonov-Bohm oscillations. The one that we should look for, so regular electrons can also do this because regular electrons are still quantum particles and they have phase. The one that's signature of the topological surface state is the one in half flux quantum. And by tuning the Fermi level, so here is a plot of temperature, but you can tune the Fermi level through the direct cone, and you can see the evolution of this peak, and then can say something about the nature of the surface electrons.
What is the dimension of the?
So this is around 200 to 300 nanometers wide. The width is generally, for the layered bismuth selenide ribbons, thinner, about 100 nanometers. The periodicity is fixed by the cross-sectional area of the wire. Okay, so I think the killer app for studying nanostructures for topological materials is this, in my opinion, and that is quantum processing using 1D wire network. So this is a theoretical framework that came out in 2011, where you have a topological superconductor in 1D confinement, right? And then all these gray boxes are local gates to locally control the chemical potential. And in this geometry, you'll get the Majorana bound states at the two ends. And by controlling the gates, you locally control where the Fermi level sits, and you can move it around. Okay, and the computation or the braiding of fermions is supposed to happen at these junctions. Okay, so you can imagine having networks of these topological superconductors, and making qubits out of topological superconductors is beneficial compared to other existing qubits because there's no phase decoherence problem. Okay, so existing qubits, the phase go out of, there's a phase decoherence due to noise fluctuations, either thermal or electrical noise fluctuations. Here, theoretically, we're not supposed to have that problem, okay? it is possible to grow nanostructures that already come highly branched, okay? So here is a growth of lead selenide where you have a main branch that has screw dislocation threading along, and that creates a periodic stress points along the wire, and those stress points become the nucleation center for the secondary branch growth. So naturally, this structure comes in during growth for some of the systems, okay? So just to tell you where the field is, we can make topological materials. This is a tin telluride, which is topological crystalline insulator, into nanoplates, dope it with indium and induce superconductivity. And we can also play around with growth conditions to try to increase the yield of the wires. So here, this is about 250, 300 nanometer width nanowires. And again, dope it with indium and induce superconductivity. Yes?
In the very top right plot, how can the resistance
So we don't think that this is a measurement problem or the equipment problem. And actually, Professor James Williams at Maryland is working with us in measuring these. So this is actually my work. So Professor Williams is measuring these materials. And we think that there's a competing, there's a competition between regular S-wave-like superconductivity and P-wave-like superconductivity. And there could be fluctuations due to the competition. That's one of the working theory right now we're trying to verify. Okay, so I hope that I motivated enough as to why we should care about studying these quantum materials at the nanoscale. And now I'm going to tell you how to grow them, okay? So vapor, liquid, solid growth, okay? So vapor, liquid, solid growth means all three phases are involved, okay? Vapor phase, solid phase, and liquid phase. I'm going to use silicon nanowires as an example. It's a classic VLS case. We're going to use gold nanoparticle as a nucleation center, as a growth catalyst. Okay? So let's look at the gold silicon binary phase diagram. Here's a eutectic point. If you have about 16.6% silicon, then this gold silicon alloy will melt at 363 degrees Celsius, the deep eutectic point, okay? So at this composition, melting temperature is pretty low. So what do? You have a gold particle, you're gonna decorate it, your growth substrate, then you're gonna heat it, right? And let's say we just heat it to about 400 degrees Celsius, something above the eutectic point. You're going to then introduce silicon vapor, so usually it'll be in the form of silane, okay? And the silicon will be then dissolved into the gold. Silicon will continuously be dissolved into the gold until you reach supersaturation, right? When you reach supersaturation, gold can no longer take silicon atoms and keep it in the liquid state, right? And then the solid phase will nucleate out. Okay, that's a classic homogeneous nucleation and growth picture. Okay, so you've reached the saturation point. Out comes the solid phase of the silicon, which can no longer be in the liquid gold droplet. Okay, and you continuously supply the silicon vapor, which then goes through this liquid gold silicon liquid droplet, and you continue to grow your silicon nanowire segment, okay? So that's the VLS part. Vapor, silicon vapor, liquid, the gold silicon liquid droplet, solid, okay? The nanowire. And the surface balance right at the triple junction, right? Where the vapor, liquid, and solid meets right here, that can determine quite a bit the morphology of the nanowires and sometimes even the crystal structure. So for silicon nanowire, it's a simple case. It's a single element system, only one crystal structure. But if you imagine growing gallium arsenide or zinc sulfide, then it could change between wurtzite to zinc plane structures, depending on the surface energy balance right at the triple junction. Okay.
I have a question. How much gold actually is left over in the silicon wire? Is there any at all?
There are gold atoms in it. I don't think I have a quant number that I can say, but people have done high resolution STEM scanning TEM work and shown gold particles embedded. So usually for silicon nanowires, gold particle is a terrible catalyst to use because gold really kills the transport properties in silicon nanowires. So people have tried using other ones like copper or palladium. You can look at the binary phase diagram yourself between silicon versus some other metal, and basically as long as the eutectic point is low enough and there's silicon that will be dissolved, then it should work as a catalyst. Yeah. Okay, so in terms of a setup, a lot of times people use just a single or two-zone small furnace. You're going to have a quartz tube, put your substrate that created gold particles, and you're going to introduce your gas vapor. Silane for silicon nanowires. Intrinsic silicon is pretty useless because you don't have that many intrinsic carriers. So you need to dope it so that you have activated carriers, right? So you can use diborane or phosphine as your dopant source, where you then co-flow the source and the dopant gas together. And you're gonna have a flow controller to control the flow rate of these gases. So that's controlling the rate at which you're supplying your source or dopant gas, and pressure. And you pump it out. Okay, so here is an SEM image of the gold particles and long and a high yield of silicon nanowires at the end. You can expand. So VLS actually, when we were growing carbon nanotubes in late 90s, same thing. We would use, let's say, metal catalysts, iron nanoparticles. You flow carbon-containing gases at high temperature so that these gases will decompose, right? And then the carbon from these gases will be soaked into these metal catalysts. Again, supersaturation, and tubular structures can come out. And you can somewhat control the diameter of the nanowires by controlling the size of the particles. Okay? So in terms of setup, this is relatively simple. This is very cheap. A few tens of K. Okay, here is a furnace. The gross substrate will be somewhere in here. Glass quartz tube. Okay. And downstream is cold trap to trap some of the toxic materials, and into the solid phase out to the pump. Here is a gas source that comes in. Yeah? What is a characteristic of VLS growth? If it's a strictly vapor liquid solid growth, then the diameter of your nanowires are strictly determined by the initial size of the metal particles. Okay? So you can then select different size metal particles, which will then give you nanowires of different diameters. When it's strictly VLS growth, this is the case. Okay? We often get single crystalline nanowires. Diameter is controlled by the diameter of the catalyst. Okay? You can now expand this growth to do heterostructures. So one natural expansion is that you switch your source gases. Okay, you grow segment A with a gas source A, you switch that off, flow the different one, B, and you can do AB. So you can then make quantum wells in this way and then study luminescence or do band gap engineering. People have done that. You can also play with the growth conditions so that instead of promoting an axial growth, you promote a radial growth. Okay? So first, you grow your core nanowire, okay? And then instead of going through the metal nanoparticle for the shell material, you're doing a direct vapor to solid deposition on the side of the wire, and then do a core shell structure. This is also possible. And you can control the growth conditions, which usually is temperature, flow rate, and the pressure. okay? And try to manipulate so that the growth conditions are more axial favored or radial, okay? So here's an example of germanium core with a silicon core shell nanowires, okay? So PN junctions, people try to make PN junction solar cells using nanowires. You can then decouple the absorption length for the light from the recombination length of the electron hole pairs. So then people did this core P, let's say, shell and PN junctions, so that radially the length is pretty small at the nanoscale, so you don't recombine the electron hole pairs. But the wires are pretty long, so that the light absorption happens along the length, and you're going to put it a periodic array of the nanowires so that you also set up some photonic modes, which helps to enhance the light absorption. I showed you at the beginning lead selenide highly branched nanowire structure, where there it was the intrinsic stress points along the central branch that promoted the secondary branch growth. But you can also decorate your central branch with secondary particles and then try to grow the branch. Okay, so at this point we don't really have a control as to exactly where we put the nanowires, but here's a proof of concept that this works. Okay. This was an example I shown you before, where here we're not using any secondary metal nanoparticles, but rather the dislocation that's threading across the central branch has a periodic stress points that act as nucleation centers. Okay, so intrinsic silicon is not so useful functional material. You need to dope it so that either you have an acceptor level or donor level, so that you activate it very easily, right? So for the nanowires, you should also dope them. And this is particularly important for topological insulators or topological crystalline insulators, because intrinsic materials have a lot of vacancy defects that's hard to control. So you can imagine then doing charge doping to compensate for those vacancy dopants. So I would say that there are about 3 ways to do it. One is co-vaporization. So you're flowing silane at the same time with borane. Okay. You could try to do it after post-growth. You've already grown silicon nanowires. Okay. Then you're going to flow your dopant. Or you can also use metal catalysts. Okay. So a friend asked, does the gold atoms get embedded in the silicon nanowires? Yes, it does. So you can now flip it around and think about using a metal catalyst, which you want to actually dope your wires with. Okay. One thing to consider in nanowire growth is that this is somewhat of an open system growth. You're flowing gas, okay, through the system. Okay. So this is quite different from bulk growth, where you will mix the known ratios of your materials, right? And then you seal it, and then you're going to anneal it. So you know that your materials are there. It's not going anywhere. Okay. That doesn't mean necessarily that the dopant will thermodynamically be included. It could still be phase separate out, but it's still there. But here, this is an open system. So the kinetics and the thermodynamics are quite different from bulk. Okay. So example of post-growth. First, grow nanowires, silicon nanowires, and then use BCl gas source. Just basically subject these nanowires through this gas at some elevated temperatures. Question: if you did this post-growth doping, how do you think the doping profile will look like? In terms of the cross-section, will the dopants be uniformly distributed in the wires, or do you think that it's uneven? Uniform. Uneven. Yeah, it's often uneven. Why? Well, I mean, the true answer will be it depends on the system. But you can imagine the dopant atoms have to diffuse from the surface to inward, right? So given the time and the temperature, that diffusion process can be very slow or needs a high thermal activation, okay? So often the doping profile is very uneven. Higher concentration of dopants near the surface, as you go inward, that concentration will drop off, okay? So then you say, okay, I'm gonna do codoping. So here is an example of germanium nanowires, and they're flowing the germanium hydride as well as the phosphine at the same time to grow these wires. Question here, in this case, uniform or uneven? Uniform, uneven. Yeah, so it can still be uneven. So this is an atom probe tomography where you're just like ablating your materials and doing a time of flight measurements of everything that came out of your materials and reconstruct back the three-dimensional structure. Chemically very sensitive because you're doing somewhat of a mass spectroscopy as a function of time. Here is the phosphorus. Okay, you're doping phosphorus. Here is the phosphorus doping concentration. Again, inhomogeneous. High on the surface, drops off as you go to the core. Okay, so in terms of thinking about applications for nanowires, doping profiles or how to dope uniformly is a big problem. Okay. Gold atoms in silicon nanowires. Using gold as a growth catalyst, you can see here, this is now scanning transmission electron microscopy image in annular dark field detector of a silicon nanowire, and all the bright circles are gold atoms that are embedded. Yeah?
Just regarding the last slide, is there any success in using annealing to evaluate the dopants?
I'm sure people try that. Yeah, I mean, I've also read some papers where that's what they do and claim that it distributes. But I think it's somewhat hard. You have to do it very carefully to really know whether or not that's true. So you can do some kind of a capacitive measurement, maybe as a function of frequency even, and then see if the assuming a uniform dopant profile versus radially changing dopant profile, what would you expect, right? I think that would be the most accurate way to do this. Atom probe, in terms of sensitivity, this isn't going to compete against transport measurements. So the metal catalyst will be incorporated into the nanowires a little bit, okay? Because solubility is not zero into silicon, right? So for silicon nanowires, gold is bad. We don't want this. Now, but you can kind of use it for your advantage. So here is an example of bismuth selenide nanoribbons. Okay, so here, this is the metal catalyst. Actually, there was a secondary one here. This is the bismuth selenide nanoribbon part. And we used iron gold metal catalyst. Okay, and the hope was that some of the iron will be doped into bismuth selenide. Because bismuth selenide is topological insulator, if you dope it with magnetic dopants, it could potentially open a gap in the surface states. This is my work when I was a postdoc at Stanford. I couldn't check whether the surface gap opened or not because there was the Fermi level was still pretty far away from the band edge of the conduction band, but at least some magnetic impurities were embedded in the nanowire. So we could see the condo behavior. Instead of using iron as a metal catalyst, you could also do codoping. So here, we're introducing vapor of bismuth selenide not through the gas form at the beginning, but actually by doing a sublimation of the powder. Okay, so this is a solid powder. You're going to heat this. It's going to vaporize, vapor form. So we annealed ferrocene, okay, with bismuth selenide powder at the same time, hoping that it's going to get the ferrocene will decompose and the iron will then get into the bismuth selenide. Depending on the precursors you use, the growth can be different. So this actually worked, and we can show Kondo effect. When I then later used iron carbonyl instead of, probably some iron still got doped, but also the surface was decorated with full of iron particles. Okay, so the choice of precursors also is important in growth. This is using the ferrocene, different iron doping levels. So for VLS growth, it must go through the metal catalyst. Okay. Strictly VLS only go through the metal catalyst. Oftentimes, there's a side growth that happens by vapor directly going to solid transition, vapor-solid deposition. That's why for bismuth selenide, bismuth telluride nanoribbons, generally the width of the nanoribbons are much larger than the size of the nanoparticles because there's a constant side growth that happens. So in that case, if you want to be very pedantic about it, you wouldn't call that a VLS growth. And maybe you would call it as metal catalyzed. Still the metal acted as a nucleation center to catalyze the growth. So you would call it metal catalyzed CVD, chemical vapor deposition growth. Okay, so this method is quite versatile. You can grow quite a number of different topological materials this way. Bismuth selenide, bismuth telluride. Now, if you don't use metal particles, because these are layer structures, you're going to do a physical vapor to solid deposition on the growth substrate. You can alloy them. Okay, so here's a mixture of selenium and tellurium. Generally, the way you would do it is that you would mix the two source powder together. Okay, so you can do it on the anion side or the cation side. Okay, just a little bit of a detour on tin telluride. It also works for tin telluride. This is topological crystalline insulator. Tin telluride source powder, gold particle decorated substrate. You get a wide range of morphology on your growth substrates. It's cubic. Tin telluride is cubic. So some plates, okay, wires. This is metal catalyzed. I was using gold nanoparticles. If you don't use gold nanoparticles, you're gonna grow cubes. It makes sense. It's cubic. So this is what you should expect. Okay, we mentioned this. Okay, topological superconductors. So first, about making topological superconductors. Okay, two approaches so far experimentally. One is you just make the topological material superconducting. So if the bulk of the topological material superconduct, because the surface is right next to bulk, by proximity the surface will superconduct. We can do this. So for bismuth selenide topological insulators, you can insert copper in the empty spaces at the van der Waals gap, and the superconductivity can be induced. So we've done this in bulk crystals. I think in thin films and nanoscales, we haven't really achieved this. For tin telluride, I liked tin telluride a little bit better because here you need a right amount of copper intercalated. Here, as long as you dope indium at any doping level, you will enhance the TC. So around 4 to 5% indium doping level, TC is around 1.7 Kelvin. Okay, again, the bulk is superconducting, so by proximity the surface will superconduct as well. Another way that's popular, and this has been really successful in spin-orbit coupled nanowires, is to put superconducting contacts onto your material, right? So that by proximity to that superconducting metal contact, that area will then superconduct. So this approach has been tried on topological materials, okay, but more successfully in spin-orbit coupled nanowires. Now, if you think about these two different approaches, right? You just make the bulk of the topological material superconduct versus you put a contact. I think there's a benefit of going with this system. So in this case, you have to make sure your superconducting contact is very good. Okay, this actually we can do this. Maybe this is not a problem. But if you actually use spin orbit coupled nanowires, there's some added complexity. To be in a topological superconducting phase, you have to tune the Fermi level and put the Fermi level at the right place, which means that you need now local gates everywhere, right? Also, the topological superconducting phase is not precisely determined. It's a range of the superconducting gap and then the Fermi level. Okay, so there's a little bit of a window in which it's going to be in topological superconducting phase. So in terms of thinking about this from engineering perspective, this actually creates a lot of complexities. One, you need a lot of gates to tune the Fermi level. Two, the criterion is not precise. So if you're trying to build tens or hundreds of qubits using spin orbit coupled nanowires, I think the architecture, hardware-wise, can be quite complex. For making topological materials itself, so yes?
In figure D, can you call that the superconducting gap if the spectrum doesn't go to zero?
This actually is not my work, so I don't actually remember the details of this. So I would advise you should look at. This is one of the Koban-Evans early papers. Yeah. So he has a series of papers on spin orbit coupled nanowires, and there's also a Nature Review Materials that came out either 2017 or 18, okay, with him as one of the authors. So that actually summarizes all of their works. So I think there's a benefit of making topological materials itself superconducting because one, you don't have to worry about putting good superconducting contacts. Two, you don't have to tune the Fermi Fermi level. As long as you apply a magnetic field, irrespective of where the Fermi level is, it's going to be in topological superconducting regime. And the criterion is precise. So from engineering perspectives, I think that it gives you a better handle. Anyway, so the point is that we're trying to get there now. Okay, so we have 20 minutes, so I'm going to briefly go through two-dimensional materials. Okay, the primary choice is chemical vapor deposition. Okay, there's also MOCVD, metal organic chemical vapor deposition, MBE, molecular beam epitaxy, right? So those actually are more sophisticated growth tools that give you more precise growth. Thus, you can make heterostructures, but here I'll just cover CVD. We all know that two-dimensional materials are interesting because their properties, electronic properties change. So Dirac physics was fascinating when graphene first came out. Okay, maybe you guys all think that that's very normal, but when it first came out, this was mind-boggling. This was fascinating. Okay. Okay. Indirect to direct semiconductor, and topological insulators are also layered materials. So 2D materials, we think they're interesting. Transition metal dichalcogenide, like molybdisulfide, has been studied about a decade, since around 2010, okay? So nearly about 10 years. But it goes way back, right? So chalcogenides, okay? Chalcogen is oxygen, sulfur, selenium, tellurium. Usually oxygen ones, we just call it oxides and separate them out. So chalcogenides are the ones where we got these three elements in it. If it's a transition metal, the chalcogenides, you would have a metal side to be a transition metal. Okay, there are a whole class of chalcogenides. They're layered structures. They were very interesting. We studied a lot dating back quite a bit. Charge density waves, spin density waves, superconductivity, two-dimensional superconductivity, competing orders between the density, charge density waves, and superconductivity. Play with intercalation to tune the superconductivity, to find out that this was a two-dimensional superconductivity, to tune the charge density waves at which it emerges. Okay. Why are we interested in these materials again? For one, we were able to now include spin orbit coupling into our calculations, and that's when we found out that there are all these topological materials that exist that we didn't know before. Two, we can make into monolayers and then heterostructures by stacking different ones, so we can make artificial design-specific materials. So that's why we're take interest in these materials again. These are via semi-metal candidates, so again, topological materials. We like this because they come in metal, insulator, semiconductor, so you can make functional devices. Usually, if you're a physicist and you are more interested in transport measurements, you're going to just exfoliate. That's simple. You can get clean samples. You're going to cap it with a boron nitride. You go and measure, right? If you're chemists or you're engineers and you're thinking about scaling up, you could do chemical exfoliation. That's a form of intercalating the solvent molecules into the layers of your two-dimensional materials, and then you're going to sonicate, so give some energy, and then the layers come apart. Okay, so it's chemical exfoliation. Those will be top down, or you can grow chemical vapor deposition. So graphene was as a first example. Here you're going to use metal as a catalyst again, but let's say you're going to have a flat nickel or copper thin film layer. You flow your carbon-containing gas, okay, so methane, for example, or ethane, anything that's carbon-containing. The gas will decompose. Carbon will be soaked into your metal layer. You cool it down. As you cool down, you're going to reach supersaturation, right? Because the solubility limit is temperature dependent, and then the graphene will emerge because it can no longer be inside the metal. So that's still one of the popular ways to grow graphene. You can also do CVD growth of hexagonal boron nitride. So we use hexagonal boron nitride to encapsulate a lot of our interesting two-dimensional materials. So here, again, you're going to use metal foil as your growth catalyst. You're going to flow ammonia borane, okay? Ammonia borane is sublimated at about 120 degrees Celsius, okay? As it flows inside here, it's very high temperature. This is going to decompose. Again, you soak your material, your metal, you cool it down, then hexagonal boron nitride will emerge. The quality is not as good as bulk, but this can happen, yeah.
What's the rate of gas flow?
Here, they also use additional argon-hydrogen mix as a carrier gas. So mostly you have a lot of this compared to this, and this was kept at 200 SCCM. Initially they also clean the furnace and probably do some treatment of the copper at 500 SCCM. Okay, 15% volume hydrogen mixed into the argon. So one thing, black phosphorus, people study quite a bit. This actually has a band gap, unlike graphene, and the mobility is fairly high, around 1,000. It's better than molybdenum disulfide. Molybdenum disulfide has a band gap, but the mobility is pretty low, around 100, let's say. So it's interesting material. You can't directly grow black phosphorus, CVD. You first grow red phosphorus, and then you then anneal under pressure and convert it into black phosphorus, okay? So one way to do it via CVD is you do a chemical vapor deposition of a red phosphorus, okay? So heating the red phosphorus, it vaporizes, come to the cooler zone where you have a substrate, you condense and make a red phosphorus, and then we put it in diamond anvil cell, pressurize it, anneal it, and then convert it into black phosphorus, okay? Now, but the one that we all know more about is, let's say, the hero material molybdenum disulfide, right? So this was like the first, I guess, paper to show single layer transistor behavior out of a molysulfide. There's a transition, right? As you're shifting around the band edges, the indirect band gap becomes a direct band gap, and you can see the quantum confinement effects here, right? The band gap increases as you decrease the layer number. The most popular way to do this is you introduce sulfur and molybdenum precursors in a powder form and you vaporize. For the sulfur, you would use elemental sulfur, okay? For the moly, you could use moly oxide, moly chloride, okay? Different precursors. Different precursors have different chemical reactivity, okay? So moly chloride, I think, is better than moly oxide, for example. sulfur vaporizes at low temperature, okay, around 80 degrees Celsius. So you're not going to actually put those two right next to each other because molybdenum dioxide vapor pressure is low. You have to heat up much higher, around 700 or 800 degrees Celsius. So generally, these two will be heated to a different temperatures. And you will put a substrate pretty close to the molybdenum dioxide, okay? And you heat it, maybe you flow some inert carrier gas. These two in the vapor form will react to form molybdenum sulfide and then will condense onto the substrate, okay? And then you can make these flakes or thin films. This growth is very finicky. So if you've never done it, but you know this can happen because there are thousands of papers that report CVD growth of molybdenum sulfide, you have to know a couple of things. One is that the vapor transport of molybdenum oxide is extremely poor. So maybe it vaporizes, but it doesn't get transported a lot. So that means that the location of your substrate should be pretty close to your moly precursor, okay? The other is that even though the molecular ratio of molybdenum sulfide is 1 to 2, you have to load a lot of sulfur, like 1 to 2,000. The reason is, again, because the transport of molybdenum oxide is very low, at the local environment just above the substrate, what matters is the local vapor pressure right here, right? And then you want that to be 1 to 2, and that can be hard to do. So one way to combat that is that you just load up the sulfur. Sulfur is cheap. Just put a ratio of 2,000 to 1. As long as you do that, you'll get molybdenum sulfide. This is actually a stepwise sulfurization. If you're using molybdenum dioxide as your precursor, you're going to first reduce this to molybdenum dioxide, okay, and then a gas. This molybdenum dioxide can be further reduced to make molybdenum sulfide, and then you can further reduce the molybdenum sulfide to molybdenum sulfide, okay, and then you can actually watch these stepwise reactions happen. This paper was pretty heroic paper. This came out last year where they grew all of these different chalcogenides, okay? Usually elemental precursor for the chalcogen, sulfur, selenium, and tellurium. For the metal part, it could be the metal oxide or metal chloride. And they show a whole wide variety of materials. Okay. This is one of the few papers where I feel like having all these names kind of maybe make sense. And sometimes I wonder why there's so many names on the paper. But here, you can kind of imagine, okay, every person does 1 or 2 materials.
Question about this very quick. Were they able to characterize the crystal structure type for all of them on this atomic?
I think they did Raman. I don't know if they did like for all of them. Some of them they also did like TM type characterization. Whether they did it for all of it, I have to look into supplementary again. Yeah.
Probably a very big substance.
Yeah.
Is that all of them, or how many are there? Is that the whole lot? Did they do the?
Oh, so I think the ones that are colored.
So that's almost all of it.
Yeah. So here, they actually used salt to assist the growth. They literally used salt, okay, sodium chloride, where they mixed sodium chloride with, okay, their metal precursors. So you ask, what is the role of salt? It's like asking, what is the role of transport agent in CVT growth? We know that you want to add transport, but what does it actually do? At least I don't have a good sense of what it does, other than, yeah, it assists transport. So here, one hypothesis is that the salt grabs the residual carbon that is inside the furnace, okay? And why does it matter? Because working theory, I don't think this has been verified, is that if you have carbons, they'll come down and then stick at the edge of your chalcogenide and terminate growth, Okay, so using salt enables growing large flakes. That's one working theory. However, salt is very bad if you talk to semiconductor industry. That's impurities. They don't want it. Okay, so yeah.
Is that something they just found empirically, or known that salt can be used?
I think before this work, I haven't. It wasn't generally known.
But it's not a salt flux per se, right? In this case.
What do you mean?
Like sometimes you do crystal growth in salt fluxes like this in chloride or something. But we melt it. You know?
So the salt definitely melts.
Oh, okay.
Because you're heating it. Yeah. So I wonder, whether they were inspired by that. Yeah. 2 minutes. Yeah. I'm gonna skip all this actually. So yes, I'm gonna skip this. One thing is that sometimes you want to think about thermodynamics versus kinetics or other effects that affect your growth and the resulting morphology. So for example, if you use moly oxide and sulfur, you're going to grow these plates, okay, where the layers are laying flat, the substrate. Now, there's another way to get moly sulfide, and there will be, you just have a metal film and you sulfurize it, okay? You react the metal with sulfur, and then it becomes moly sulfide. If you do that way, actually layers stand vertically instead of laying flat. However, the growth conditions are very similar, meaning the thermodynamic conditions are similar. Thermodynamic energies are similar. So how is this possible? Because you can imagine that the surface energy that the system has to pay in this situation is so much higher, right? Because these are all very volatile edge states. It turns out the reason why it does this is that the initial molybdenum has to expand to include sulfur into it, right? So there's a lot of strain and stress that gets built during the expansion. So it would rather pay surface energy and grow freely this way versus trying to grow this way and then build a lot of strain, okay? So here, thermodynamics and kinetics are not the reason for the different morphologies, but rather it's the volume expansion that's in the system. Do you have a question?
What growth conditions do you check with the AND?
Similar. So you would heat this. It happens in any range, anywhere between 6 to 850. You will still get these two different morphologies anyway. So you're heating it, and you're heating the sulfur at around 80 to 100 degree. This sulfur, and then it'll vaporize using argon as a carrier gas to carry.
But is it possible in this case to get mixture of two?
Yeah. So if your film is sort of thin, if your film is very thin, you're going to get a lateral growth of a layer laying flat. If the thickness is somewhat intermediate, then you'll have layers that are vertical or mixed polycrystalline. Yeah. So this is the picture. Okay, I think I'm nearly done. So we like nanoscale because we want to enhance the surface states and then their emergent properties, but there are a lot of problems with the nanoscale materials, right? One is you have enhanced surface properties. That applies for both good and bad, right? So for bad, surface oxidation is always a problem, okay? Surface oxidation could mean that you have a bad contact, you have to take care of this. Could also mean that you create a lot of surface trap sites, which will then degrade the transport measurements. And if you have surface defects, those will be pronounced in the transport measurements as well. So one example was measuring the magnetoresistance of tungsten ditelluride, and as you thin it down, the magnetoresistance actually gets pretty small. And the reason is purely due to surface oxidation. Okay, so here, this is a tungsten ditelluride sitting on silicon oxide substrate, and it's got about a nanometer oxide layer, which then enhances scattering. Okay, so the mobility drops quite a bit, and because the mobility drops, the magnetoresistance drops. So we covered all this, and any questions?